Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on modeling heteroscedasticity. And in this lesson, I'll introduce an extension of the arch model, the so-called generalized arch model, or GARCH. The arch model, while easy to understand and interpret, it has some limitations. The arch model is rather restrictive in that the model assumes that positive and negative shocks have the same effect on volatility because it depends on the square of the previous shocks. In practice, however, it is well known that many economic and financial indicators, but also other phenomena or other measures with time dynamics, respond differently to positive and negative shocks, particularly because negative and positive shocks may be of different nature. For example, some negative shocks can be political or environmental, while some positive shocks can be economic-driven. Moreover, arch models are likely to overpredict the volatility because they respond slowly to large isolated shocks to the return series, and because when modeled with arch, large variance effects disappear quickly, certainly no longer than the arch order, the specified arch order. Given that the impact of high variance may last for a longer period of time, we would prefer a model in which the impact of large variance can be expressed for much longer than the order of the model equations, of the order of the arch. Last, the arch model does not provide any new insight for understanding the source of variations of a time series. It provides a mechanical way to describe the behavior of the condition of variance. It gives no indication about what causes such behavior to happen. Such limitations can be addressed with a more general model GARCH or extensions of this model, as we'll see in a different lesson. GARCH stands for Generalized Autoregressive Conditional Heteroscedasticity. The intuition behind this model is that it is a weighted average of past squared residuals, but it has declining weights, which never go completely to zeros. Hence, it models the impact of large variance for a longer period of time than the specified orders. The most widely used GARCH specification asserts that the best predictor of the variance in the next period is a weighted average of the long-run average variance, the variance predicted for this period, and the new information for this period, which consists of the most recent squared residuals. Such an updating rule is a simple description of an adaptive or learning behavior. For ease of understanding, I'm presenting on the slide the simple GARCH1 model, which often is sufficient to model heteroscedasticity. The conditional variance sigma t squared is modeled using the lagged squared noise process zt-1, similar to the arch model, but also includes additional lagged relationship with past variability through sigma t-1 squared. This addition allows for modeling the impact of the variance for longer than an order 1 arch model. More generally, a GARCH M and N with orders M and N, that is of AR order M and an MA order N, is when the conditional variance depends linearly on the lagged squared noise process through zt-1, zt-2 up to zt-m, but also through the past variability through sigma t-1 squared up to sigma t-n squared. Thus, the interpretation of the two orders is as follows. M refers to how many autoregressive lags or arch terms appear in the equation, while N refers to how many moving average lags are specified, which here is often called the number of GARCH terms. This model was introduced by Boleslav in 1986. If ZT is modeled by a GARCH model, then ZT squared is an ARMA process, but not with IID, or independent identically distributed white noise. The volatility of the ZT squared cannot be observed fully since it depends on the lagged ZT squared time series. In this example, it depends on ZT minus 1 squared. Thus, we express ZT squared as the sum between the volatility and omega t. Starting with this formula, we can replace sigma t minus 1 squared with ZT minus 1 squared minus sigma t minus 1 squared. Separating the terms in ZT minus 1 and omega, we have an ARMA 1-1 process. Adding together the terms with ZT minus 1 squared leads then to an ARMA model in ZT minus 1 squared, where the error coefficient is gamma 1 plus beta 1 and the MA coefficient is minus beta 1. Given that Yt is the sum between the mean mu and the Garch process of orders 1 and 1, then Yt is stationary if its expectation mu is constant for all time points. The variance of Yt, which is equal to Zt, is also equal to Zt, to the variance to the expectation of the Zt squared, is computed as on the slide. From this derivation, we have a condition in the marginal or unconditional variance of Yt and the Garch coefficients gamma 0, gamma 1, and beta 1. Specifically, the unconditional variance is equal to gamma 0 divided by 1 minus gamma 1 minus beta 1. For this variance to be finite and positive as required for stationarity of Yt, we need to have that 1 minus gamma 1 minus beta 1 to be positive, or the sum of the two coefficients to be smaller than 1, and that the two coefficients are also positive. The last condition is that the covariance between Yt and Yt minus 1 is 0. That is, Yt and Yt minus 1 are uncorrelated. Note that this does not mean they are independent. In fact, for a Garch model, they are not independent. Last, I'll point out that the second and the third conditions will be different for other orders of the Garch model. These are some important characteristics of a Garch 1-1 model, one of the most popular models for modeling heteroscedasticity. The first condition was derived in the previous slide, and it guarantees stationarity. The second characteristic is that Garch models capture volatility that comes in clusters, that is, periods of high volatility followed by periods of low volatility. Last, the Garch model has heavy tails measured by the quartices, that is, the quartices is larger than 3. If we have this condition on the Garch coefficients. A heavy tail distribution means that Garch can capture outlying periods of large volatility, large variability. We can expand the Garch model by considering joint models, for example, ARMA Garch models. For an AR1 Garch 1-1 model, the model equations are on the slide. Yt is modeled by an AR1 model with error coefficient phi, whereas the noise Zt is modeled by a Garch 1-1 model, which means that the variance of Zt sigma t squared follows the formula of a Garch 1-1 model. Another example provided on the slide is the ARMA 1-1 with Garch 1-2 joint model for illustration of such joint models. The estimation of the parameters of Garch models is the maximum likelihood estimation approach. The parameters to be estimated are the coefficients gamma 0, gamma 1 up to gamma n, and the coefficients beta 1 up to beta n for a Garch model of orders m and n. If we assume normality, the conditional likelihood function of Yt given a past history up to time t can be expressed as a normal distribution with mean 0 if the mean of Yt is 0 and variance sigma t squared. The PDF, the probability density function, is as on the slide. If we replace sigma t squared, the conditional distribution, the conditional distribution, is now a function of the GARCH coefficients. As we discussed in the first lesson of the first lecture of this course, we commonly estimate such models by using a conditional likelihood, which will be the product of such conditional distributions. As you would expect, maximizing the resulting likelihood function is very complicated, requiring numerical algorithms. This is why when we estimate GARCH models in R, it can take a minute or two to get the fitted model. There are also different numeric algorithms that can be used. Some can be slower, but reaching convergence. Some are faster, but not guaranteeing convergence. This is the case for the two implementations of the GARCH model as discussed in the previous lesson. In summary, in this lesson, I introduced the more general GARCH model, the generalized arch, which will apply with a data example in the next lesson. Thank you.